Okay, moving on with the next technique for finding volume. That would be when we start revolving things. So this is going to get a little crazy. However, if you're following me with what we've done so far, if, for instance, you understand the concept of a representative rectangle, this will be pretty easy, theoretically. Knock on big wood. Okay, here we go. So we're going to talk about the disk method today. By the way, just talking schedule-wise, today disk method, Wednesday the washer method, Friday work on review assignment, come back from spring break, have a day to get caught up, test on, I think it's Thursday of that week we come back. That'll wrap up chapters. No. Yes, that'll be our final test, and then the following week we start review. Woohoo! Okay, so you should be able to find the volume of revolution using the disk method. Eventually, we're going to come back to the same slideshow and do the washer method. I put it all together in one slideshow. And then you should also be able to do something nice for a stranger today. A complete stranger, not somebody you kind of know. Okay, so here's what we're gonna do. We're gonna take all these weird shapes we've been playing with already, and we're gonna start spinning them around axes and making all kinds of funky shapes. Your job is going to be to calculate the volume of those funky shapes. Okay? So we're going to start with this idea. I'm going to take a rectangle, and I'm going to spin a rectangle. And when I spin a rectangle, I get a disk. You might know that as a cylinder, but we're going to call it a disk. Okay? What we're going to do, however, is we're going to shrink W. We'll get to that later. But first of all, let's just make sure you understand that idea. If I spin a rectangle around an axis, I get a disk. Okay. The radius of the disk is the same as the height of the rectangle. The height of the disk is the same as the width of the rectangle. So if you think of that as a cylinder on its side, you understand what I'm talking about. Any questions? Pretty easy, yes? Good. So we only have one thing to do, and that is find the volume of one disk. Once you get that, the rest is easy peasy, lemon squeezy. So let's do that.
Wait, so the radius of the disk is equal to the height?
The radius of the disk is equal to the height of the rectangle. And the height of the disk is equal to the width of the rectangle, which in a couple minutes will become a moot point because we're going to have a very, very, very skinny rectangle as we've been drawing in our pictures.
So you mean like height of the disk as in if it was like
if you flip it over, yeah. If it looks like a Pringles can or a tuna can or some type of can, Franks and beans, whatever you got in the can. Okay, so there it is summarized. Pi r squared times W. Pi r squared is the area of the circle. W is the width of the disk. That should look familiar. It's kind of the formula for a cylinder. Pi r squared times height. We just replace height with width, and we're in business. And it's actually going to get easier than that when we talk a little bit of calculus. This is just a basic, if I was looking for the area of that big honkin' revolved disk. We're going to make it easier in a second. Okay, so this is what you get when you're looking for the volume of a figure. You take a whole bunch of those rectangles and you get that solid. Now that's not very good for us because you'll see that there's a whole bunch of wasted space there in the first picture between the rectangles and the actual curve. And we've talked about this. We don't want that wasted space. This would be nice as an approximation, but this is calculus and we're not happy with approximations. We want exact answers. So how do I get it more accurate? Mason.
Make them skinnier.
Beautiful. Or, it's kind of the same thing, just another way of going about it. Make the rectangle skinnier or increase the number of rectangles, which would then make it skinny. Good. If those rectangles get really, really skinny, we lose a whole bunch of this wasted space, and we get really close to the exact area, exact volume, which is what we're looking for. How do we do that? It's real simple. We just change W into dx. So this is our goal. If we do an approximation, we get this weird looking steppy thing, We don't want this weird looking steppy thing. We want this nice, sexy, curvy looking thing. Curvy, good. Steppy thing, not good. Okay, curvy, good. So again, we'll get that by shrinking the width of the rectangles. We're going to have a whole bunch of rectangles. In fact, how many rectangles will we have? Infinite. And how do we add up a bunch of infinite things? Integrals. Because it's an accumulator. Okay, so Mason already answered this question, so I'll just click quickly through this. Oh, this will be fun. For those of you that are visual learners, I have these for you. Okay, so ignore the guy in red. Now, the nice thing about the guy in red is we don't have to do that anymore. We used to, and people normally start to cry. We don't have to teach the shell method there, so just pretend it's not there. Here's my disc. Sorry, here's my rectangle. I have it horizontally just because it was easier to animate, but if you're bothered by this, turn your head sideways. Okay? So, if I revolve that puppy, you see it spins and makes a nice, pretty disc. Okay? Easy? Yes? Yes? Okay. While I have this open, let me give you a precursor of what we're going to do when we get to the shell method. Stop. We're going to take this little guy. Whoops. We're going to take this little guy and move it off the shape. Hold on, please. Display. Display. Get rid of that. No. Display. Erase traces. And then revolve. Ooh. That's called a washer. We'll do that on Monday. No, today's Monday. On Wednesday. Eric, question.
Are we ever going to do it when we flip like that, the other, like, over the x-axis? That whole shape, so it becomes a sphere?
No, that because then that becomes a shell. And trust me, you don't want to go there. We don't have to teach these anymore. So we're not going to. It's kind of mesmerizing, isn't it? Okay, but anyways, this washer thing, we're going to wait till Wednesday. Today we're just doing discs. So let's stop this bad boy. Go away. I don't care about you anymore. Don't take it personally. Boom. Okay, so this is easiest if we just dive into it. We've done the hard work already for setting these types of problems up. Okay, I've got a parabola. Faith, what can you tell me about that parabola? Is it open up or down? Up. And is it moved up or down 3, left or right 3? Up 3, there you go. I knew you'd get there eventually. It's a standard parabola that's facing up, shifted up 3. And then I've got 2 vertical lines, x equals -2 and x equals 2. And I'm going to revolve this around the x-axis. Now, you should be able to draw this and go, well, if you have my slideshow, you already see it. Never mind, I'm just going to move on. It looks like this. That yellow region is my 3-dimensional region. The blue thing is my representative rectangle. When you're drawing your representative rectangle, it won't be so thick. It'll just look like a segment. Because we're going to take the width of that rectangle and shrink it infinitely small. Okay, so we have to find the height of that rectangle, which will lead us to the area of that rectangle. How tall is that rectangle? Since my rectangle is vertical, I'm doing top minus bottom. The top is the parabola, x squared minus 3. The bottom is the x-axis, also known as 0. So the height of that rectangle is just x squared plus 3. Its width is dx. Okay, so we get that. Now all I need to do is find the volume by squaring that and multiplying it by pi. So the first part of this pi times the quantity x squared plus 3 quantity squared is pi r squared. The dx represents the w from way back in that previous slide. So again, that's why I said the thickness of the rectangle becomes a moot point because we're just going to shrink it down to infinitely small. Does that seem like a difficult thing to do? No? Good. Trying to stay with the KISS method here to make your lives a little bit easier. Then I have to ask myself the next question. I'm taking rectangles from where to where? Well, I'm taking rectangles moving horizontally. My first rectangle shows up at -2. My last rectangle shows up at 2. So therefore, I put that all together into that monstrosity. Move the pi out in front because it's a constant. Make your life easy. I will warn you, however, when people move that pi out in front, they have a tendency to forget about it. When you're done calculating the volume, make sure you've multiplied your answer by pi. In other words, if you fn in that, x squared plus 3 to the second power, from -2 to 2, make sure you multiply your answer by pi because that number is sitting out in front and it's part of the equation. You don't have to draw the three-dimensional pictures unless you really want to. I mean, it's entirely up to you. But you should be drawing this yellow picture over on the side here so that you can visualize what's happening. Now, what can change? Well, we'll talk about washers later, so that's not something we have to be concerned about. The only thing that can really change now is we can use horizontal rectangles where everything's in terms of y. It's the exact same process. It's just you have a different variable. Okay, we're done. Anybody? Do you know who the guy on the right is? Really? Nobody knows who Method Man is? Okay. Do you know what this thing is? It's a floppy disk, correct? Yeah, that's disk method man. Get his method disk method. Yeah. Wow. You know what, Eric? I don't think I've ever heard a more sarcastic clap in my life.
No, that was good.
Whatever. Okay, so again, the slideshow has more. We'll save the washer method until Wednesday, where we can start pulling those rectangles off the axis of revolution. So we're going to walk before we run here.